till now, when we have looked at gates and logic operations, we have been thinking about truth tables and trying to define the function of these gates and these operations by using truth tables. But what we can actually do is represent these functions as algebraic equations or expressions as well, um, in a very similar manner, like we do in normal maths. Like we can use algebra here as well. Okay, so to show you how this works, let me just take the algebraic equation of the XOR gate. Okay, so you remember in the previous video we looked at the XOR gate and we said that the output, let's say C of XOR gate, is written as A XOR B, and A XOR B can also be written as A B bar plus A bar B. Now again, a little bit about nomenclature. Not of B, so this thing uh, can be pronounced as not of B, right? So not is the not operation of B, or sometimes, just to simplify things, you can also call it B bar. And the reason why we call it B bar is because there's a bar on top of B, and you know that what you mean by B bar is not of B. Okay. Similarly, when you have the AND operation, we usually write it as A dot B, but sometimes, for simplification, you just write it as AB. Okay, you remove the dot and you understand that that's an AND operation there. Okay, so in this case, this is A and B not of B, or A not of A and B. Okay. Okay, let's continue then. So now let's say I want to say, okay, I want to know how this XOR gate works. Now I know how it works. So the equation has been given to me. So how do I know what the XOR gate does? So what you can do is you can again you can go from the from this algebraic equation. Okay, and this algebraic equation is called the Boolean algebraic equation. Okay, the reason why it's called Boolean is basically to denote that it is different from the algebra that you do in your maths, right? This is Boolean algebra. That means the variables in this algebraic equation can only take two values, 0 and 1. Okay, so this is Boolean algebra. And what you can do is you can say, okay, if A and B are different values, so what will we see? And I can go from the Boolean expression to the truth table. So let's just take a look at that, and hopefully uh, this will help you see how what is the function of the Boolean algebra. Okay, so you can have four combinations of AB, right? Now, if I evaluate this expression here for each of these combinations, so when A and B are 0, both are 0, so what is going to happen to this expression? A is going to be 0, right? And B bar, so B is 0, so not of B is going to be 1, plus not of A is going to be 1 and 0, right? So what I'm doing is I'm evaluating this expression for the values A equal to 0 and B equal to 0. So that's what I get. And what is that going to be equal to? That is simply going to be equal to 0, isn't it? Because yeah, A at 0 and 1 is 0, and 1 and 0 is 0. So 0 or 0 is again 0. So I get an output of 0. So let me write it. Okay, now let's evaluate the expression for a equal to 0 and b equal to 1. Okay, so a is 1, so we get 1, and then b is 1. Oh, I'm sorry, let's just go back a bit. Okay, let's restart this again. So a is 0, so you can write 0, and what is the value of b? B is 1 and not of b is going to be 0, plus what's the value of a? A is 0, so not of a is going to be 1 and 1 because b is also 1, right? And if you evaluate this, this becomes 0, add 0 or 1. 0 or 1 is equal to 1. So you get the value 1 here as your output of the XOR gate. Now let's evaluate the same thing for the expression for b a equal to 1 and b equal to 0. And what you would find is you'll have 1 and 1 or 0 or 0, and that turns out to be 1 or 0, which is also equal to 1. So we put 1 here. Now let's evaluate the equation for a equal to 1 and b equal to 1. If a equal to 1, a is what value? 1. What is not of a? Not of b, sorry. B is 1, so not of b is equal to 0. So a and 0 is 0. Now look at this. A and not of a is equal to 0 and b is 1. So again this is 0. So 0 or 0 is 0. Okay. So what you get here is again 0. And you can see that we have gone now from this Boolean expression to this truth table. And we have figured out, so basically what we are saying is you can check that this truth table is uh, exactly the same truth table as we had for the XOR gate in the previous video. But we are now representing this truth table as an algebraic expression. Okay, so there are these two different ways of representing the function of a logic circuit, a digital circuit. We also call that logic circuit. Okay, and we'll take a look at a few more things in the next video so that we can start designing digital circuits.